In this video, I'm going to show you how to find the minimum value in a binary tree. Once again, we're going to use recursion, which means we're going to break down a large, complex problem into a bunch of smaller and easier to solve problems. So, to find the minimum value in this tree, we should find the minimum in the left and right subtrees. Then we'll compare those minimum values with the value in the root, and this way we can find the minimum in our main binary tree. Now, we're going to do this recursively. So when it comes to finding the minimum value in the right subtree, we look at this root node, then we look at its left side. On the left, we have a single node tree. Finding the minimum value in this subtree is super easy. It's basically the value in this node itself. So we should compare 4 with 30. The minimum of the two is 4. So 4 is the minimum value in this subtree. Now here's a question for you. What kind of traversal algorithm have we used here? Again, here's another example of post-order traversal. To find the minimum value in the tree, we start with the leaf nodes. We pass the value of the leaf nodes up to their root, find their minimum, and then recursively pass it up the tree until we visit the root node. This is post-order traversal in action. Now let's see this in code. So here I'm going to create a private method, private integer min. We give it a node called root. And here we should find the minimum in the left subtree. So we call this method recursively and give it root.left child. This will return the minimum in the left subtree, so we store it in this variable. Now similarly, we're going to find the minimum in the right subtree. So var right equals min of root.right child. Finally, we should compare these two values with the value of the root node. We pick the minimum and return it. So here we're going to return math.min. Now this method takes only 2 arguments, but here we have 3 values. So we need to call it twice. First we call it and give it left and right as arguments. Then we're going to call it again. Now as the first argument, we're going to pass the return value of the first call. And as the second argument, we're going to pass root.value. So this way we can find the minimum of 3 values. Now, what is missing here is our base condition. What is the base condition? That is when we get to a leaf node. If we get to a leaf node, we should return the value of that node itself. Now, earlier, we implemented this logic for detecting a leaf node. We don't want to repeat this. We want to extract this into a separate private method called isLeaf. So I'm going to declare another private method, private boolean isLeaf. We give it a node, and here we return node.left child equals null, and node.right child equals null. Now we can reuse this method in 2 places. Once in our height method, and also in our min method. So if we have a leaf node, then we're going to return the value of that node. We're almost done. Finally, we need a public method for triggering the recursion. So this is a small cost that we have to pay in terms of coding, but as you can see, our implementation is super simple. So public integer min, here we return min of root. Now let's test this. Back to the main class. I'm going to call tree.min, and here we expect to see 1 as the minimum value in this tree. Beautiful. Now back to this tree. Here we're dealing with a binary tree, but this binary tree is not a binary search tree. Because in a binary search tree, all the values in the left subtree should be smaller than the value of the root itself. In this example, we shouldn't have 21 here because 21 is not smaller than 20. Similarly, in a binary search tree, all the values in the right subtree should be greater than the value of the root itself. Once again, we shouldn't have 4 here because 4 is not greater than 20. But let's imagine we didn't have these 2 nodes over here. In a binary search tree, we have a simpler way to find the minimum value. So as I told you, all the values in the left subtree are smaller than the value of the root itself. Now let's go to the left side. Let's look at this subtree over here. So 10 is the root. Now all the values on the left side of the root are smaller than the root itself, right? So if we keep going to the left side and find the leftmost leaf, we can find the minimum value. By the same token, if we keep going to the right and find the rightmost leaf, we can find the maximum value. So if you get this question in an interview, first you should figure out if you're dealing with a binary tree or a binary search tree. If you're given a binary tree, then you need to find the minimum value using this algorithm. But if you're given a binary search tree, you need to find the leftmost leaf. Let me show you how to do that. So back to our public min method. I'm going to declare a variable current and set it to the root. Now, as long as current is not null, we're going to set current to current.left child. So this way we can keep going to the left subtree. Now, at some point, current is going to be null. So we need another reference or another pointer to the leftmost child. So here I'm going to declare another variable, last, and initially we set it to current. Now, before we set current to its left child, we're going to set last to current. Now, at some point, current is going to be null, so we'll break out of this loop. And here, last is going to reference the leftmost child. So we simply return last.value. Now, if the tree is empty, this line is going to throw a null pointer exception. So we should guard against this by an if statement on the top. So if root equals null, then we're going to throw a new illegal state exception. In other words, we cannot find a minimum value in an empty tree. That's an invalid operation. So this is how we can find the minimum value. Now let's look at the time complexity of these two different algorithms. What do you think is the time complexity of this method? Here we have O of n because we have to traverse every node in this tree to find the minimum value. So I'm going to add that as a comment, O of n. What about this other method for finding the minimum value in a binary search tree? Here we're not traversing the entire tree. We're just trying to find the leftmost leaf. So in every iteration, we're throwing out half of the nodes in this tree. We're narrowing down our search. What is the time complexity of this operation? It's O of log n. Because as I told you before, if you're narrowing down our search and throwing out roughly about half of our nodes, we have logarithmic time complexity. So let me add that over here. O of log